Okay, sorry about that. Thanks, Graham, for agreeing to give a talk. As Denjo mentioned, Graham doesn't really need much introduction to this audience, but for those who might not know, Graham was a Schrodinger Fellow here up until, I think, around 2023 or so.
21, maybe.
21, okay.
22, yeah, I don't know.
Yeah.
Yeah. Yeah.
And now Graham is a professor in Maynooth College, and he's going to tell us about entanglement transitions and replica tricks.
Thanks very much, Shane. Thanks everybody for coming, and it is really nice to be back here again. So hopefully everybody can hear me as well online. So I'm going to tell you this story about entanglement transitions, and this is really a story about different ways that we can model open quantum systems. Essentially, it's trying to compare what you can get in
Andrew Mitchell says we can't really hear online. Sorry.
I can turn on my speaker here. Maybe.
I will interfere with the other ones if they can hear us. The speaker here is not the issue. Well, maybe I don't know. Maybe turn up the volume. Might have missed it. Some.
Okay, is that any better?
From Eric.
Okay, much better. Okay.
Okay, so that's good.
That's okay.
Okay, it's good. Yeah, so it's really about comparing different approaches to open quantum systems, and in particular open quantum dynamics, let's say. And so, I mean, there's lots of different ways you can model open quantum systems, but kind of the two main things that are techniques that people use is one is what we call NIMBLAD or kind of GKSL dynamics, where you model averages, density matrices going forward in time. So you're taking the average and you're modeling that average as it flows through time. And then another competing approach is taking individual trajectories. So what you're doing when you model quantum trajectories is you're modeling pure states, and you're just running it over and over and over again. And then there's some inherent randomness built into your system. And what you do is you just take your averages over all the different trajectories. And so the particular trajectory method that I'm going to focus on today is one where where the randomness comes in through kind of a Wiener process. And these are the kind of equations that I'll be running through and how they work today. And at some point I'll show you precisely how these two things are related. But then I also want to show you, how you can maybe get something else from this NIMBLAD approach. But there's a suggestion that the NIMBLAD approach can't give you all the information that you could get from all the trajectories. And so I want to show you how you can really get that. And so the motivation will be to show you how to model, let's say, a master equation, which not only gives you access to averages, but can give you access to, let's say, higher moments. So that's the motivation. So if I have an open quantum system, so this is like what would be a very simple model for a closed quantum system. And if I looked at the Hamiltonian, which is just some fermion hopping over and back between two sides, and if I look at the system over time, and it's a fully closed system, so there's no interference with the outside world, you expect this oscillation, this oscillatory behavior. And so it'll go over and back, and that will continue indefinitely. But when you start to open quantum systems, when you go to open quantum systems, you're kind of effectively dampening the system. And what happens if you look at the average dynamics, this is the blue line, this is what you get from, let's say, some kind of NIMBLAD equation. So the NIMBLAD equation would send you towards some steady state, and eventually you'd saturate, essentially where the fermion is neither here nor there. It's kind of distributed between both sides. But if you look at that in terms of the trajectory method, you look at one trajectory, the actual dynamics is very, very random and it jumps all over the place. But then what you expect is if you go to more and more trajectories and you start to model more and more trajectories and you look at the average value that you get from all those trajectories, you should start to approach the NIMBLAD dynamics. And so if you go, you can you can go to as many trajectories as you want, essentially, and there's a sense that in the limit of infinite trajectories, you would get the limit. And so some of the terminology here is that you would say that the trajectory process or that method is like an unraveling of the Lindblad process. But there are actually lots of different ways that you can unravel a process, and this Wiener unravel a Lindblad equation, and this Wiener process one is just one of those ways. So that average is gotten. I don't know if you can kind of see, but I've taken some of the trajectories and just put them in at the back, right? So there's this. They're all over the place. There's a distribution there, and you know, if you take a slice at any one point in time, you can imagine looking, counting, you know, doing some binning and just seeing where is the average of that expectation value, and you'll see you'll get some distribution, and you can imagine again in the infinite limit you could get a well-defined and nice and smooth probabilistic solution. So you have some function p, and you know another slice might give you something else, and so this is like a probability distribution of the expectation values of this particular operator or this observable that we're going to measure. But because you have a probability distribution when you have trajectories, you have a sense that you could also, not only can you calculate the mean, but you could also calculate higher moments of those particular trajectories. So for example, in this particular case, I could take any power of S. So I could calculate from this, I could calculate the second moment or the third moment, and so on and so forth. And so I have something more, right? Because I have the full measurement distribution, I can get access to these higher order pieces of information. And I don't have that on the level of the Lindblad equation. I've already averaged, and that's all I can do. And you might also understand, so if you can get higher moments, you might imagine that you can also look at more complicated nonlinear quantities within the system. So one of the things that we want to look at here in this story is we want to look at let's say the average entanglement of lots of these different trajectories. So on average, what is the entanglement of all these pure states as we evolve forward? And so like the entanglement is in principle, at least in terms of how we write it here, you can imagine taking some long winding chain. We're going to cut the chain, and we want to understand how can we write the system in terms of sums or products of states that exist in both once in A times B. And the entanglement is a measure essentially of how many of these terms that we would need in order to fully describe the system. And another way that you could describe this is if you looked at, say, the entanglement entropy. So what you do is you take a pure state, each of one of these particular trajectories that I mentioned, you take that trajectory, you make the outer product, or you make the density matrix, you trace out B, you have a reduced density matrix with rho A, and then you basically take the trace of that, or trace of rho, log rho, and then you get what you can call the entanglement entropy. And so, because you can do that for each individual trajectory, right, it actually really only makes sense if you're doing this for pure states. So you're doing for each individual pure state. You can imagine then averaging over all those trajectories, right? You can take the average entanglement of your system. And that somehow gives you information about what the trajectories do on average, right, in terms of their. And again, it's something that you can get if you have access to the trajectories, but you can't get if you're trying to just run a master equation. So this notion of entanglement transition in this context, in the context of these dynamical systems, means that you take that average entanglement entropy and you're asking the question, how does it grow as my system size grows? So I'm going to cut my system, let's say, in half, but I want to ask the question of how does this average entanglement entropy grow as I make the system bigger? So this is often phrased in terms of bulk scaling versus boundary scaling, and we know it says that bulk scaling basically means that the entanglement will grow with the size of somehow the volume essentially that I'm cutting out of the system. But it often gets reduced to things like you can do it in 2D, in which case it'd be area log versus length log, One media would be like length law versus point law. So those are the kind of questions we would ask. It seems to be that regardless of which dimension you're thinking about, people often use volume law versus area law. So the story of this entanglement transitions is, for the most part, is about 1D systems. We're asking, how does the average entanglement of a system grow as a function of the system size and as a function of basically how we're measuring. So yeah. So if I go back to the trajectories, I didn't really spell it out, but the measuring strength or the rate of the measuring strength I'm talking about here is in this parameter gamma. So I don't know if you can see it on this, it's kind of bright, but it's this bright green gamma. And that kind of determines how robust my measurement process is. If I take it very, very strong in this kind of sense, it's very much like a projective type measurement. And it's very weak, you're kind of half looking at the system, or you're weakly perturbing the system, but you're certainly doing something non-unitary at the same time. So that's how that comes in. And then these are some numerics, and this is what you might.
So you're saying you're mostly interested in 1D.
Yeah.
So when you go to your point one, does that mean you're looking for logarithmic behavior?
Yeah. In principle, yeah. In for fermions, for sure, it's kind of logarithmic scaling. So to give you an example of what it might look like on an actual calculation, the volume law phase here, and I put that in quotes, is like you see like a fairly steady increase in terms of where the entanglement saturates on average as I make my system bigger. All other things being equal, I make the system bigger, and it saturates to a different value that's higher. In an area law phase, you might see some small change, but you wouldn't see something that would eventually, eventually you would see that actually there's a finite value because of a large enough system size. And it doesn't matter how big a system is, the entanglement between these two regions A and B is just somehow limited. And that's to do with, I mean, you can kind of heuristically understand it in the sense that you're measuring so much that you're kind of impeding any kind of entanglement between the two systems, you're kind of locking it down. So it stays, it saturates at some low value that doesn't scale with the system. Another thing you can do in this game is you can look at different types of measurement processes. And this is I'm giving you this plug of this paper that we did in 2023 because it illustrates an important thing for how I got into this particular story. So what we did was we looked at two different types of measurements. The measurement on the top here was very much like what I mentioned before. You're looking on site to see if there's a fermion on your lattice at each particular point in time. And the second one was a little bit different. It was kind of, if that looking on site was like a sigma z, this was like an XX term. You were kind of looking at an operator that was distributed between two sites. I suppose the important point about this red type measurement was it didn't conserve fermion number. There's a superconducting term in there when you look at fermions, and so it broke this. It broke the U1 situation. So this was the type of thing we were trying to do, and we came up with this interesting phase diagram, and where the blue here kind of essentially indicates area of phases. So these are the different parameters. The alpha and the gamma are the two different types of measurement rates. The W is just some energy scale in the system. So what we found is that, sure enough, you can draw a line in the phase diagram, and if you can look across that line, you get something that looks like characteristic like a phase transition.
So what's the difference between M and O?
Two different operators. So M is like a sigma z, for example, and an O is like a sigma x, something like that. That's probably what it's like. So it would be like, in fermions, it would be like measuring the operator C dagger plus C, C dagger minus C, something like that. But there's inherently, somewhere in there you have two C daggers, so you're breaking your.
So sigma x, sigma x.
Yeah.
But sigma x goes with one.
No, on two different sides. Like sigma x. Yeah.
Two different sides.
Two different sides, yeah. Sigma x on side one.
Is that like a dual lattice?
Yeah. There's a duality to this that particular. That's why we chose it as well. Yeah. So but it's subtly different in terms of, because the normal Hamiltonian here has isn't quite symmetric to both of those terms, so you get a slight asymmetry in the phase diagram, which is why it looks kind of different from left to right. But if you cut along that orange line, for example, and that's a line that inherently breaks this number conserving property, you see that all the lines, there's this nice property where as you make your system bigger, they all cross at a single point, which is kind of like the characteristic that you would want to call it a transition. So you make your system bigger, but there's some kind of fixed point. And you can imagine rescaling around that fixed point, and you can derive some critical exponents or something like that. So if you have that, you can reasonably argue that you have something that looks like a transition. But what I want to point out is, this is how you can use graphics to hide stuff. But like, you see the blue line here, the blue line is where we identified the blue dots, where we identified the transition of this 2D diagram. You see, we weren't able to get it right up against the edge. So we can get it right up against the right-hand edge, which is effectively this purple here. So it's not quite up against that. And when we try to resolve the transition, when we don't break the number conservation, then we actually get this kind of thing where the lines won't go through the same point. Every time we go to a bigger system size, the crossing point between tends to drift back. And so it looks very much like when you can see these transitions when you have broken number conservation. But when you basically don't have it, there's some kind of crossover, but you couldn't call it a transition, right? So there's something that
I'm trying to catch up with the two diagrams. The right-hand side, you're showing this W and you've factorized across it by the. It's effectively plotted on the left-hand side.
Right. So effectively, this is kind of essentially going from along this line here, and we're trying to identify a point in W, let's say.
Yes.
But this is like, this is kind of a weird scale graph. But at some point here, we would like to identify where there was a crossing. And what we find is, as we make the system size bigger, the crossings tend to drift back up towards this side here. Yes. Yeah.
But you have set on your right-hand side. Have you set gamma equals 1?
Yeah, I think so. Yeah.
Oh, you have.
Sorry.
So I shouldn't even
No, sorry, I should have said that. But yeah, I think that this was the way we decided to graph it in the end.
Right.
Yeah, okay. And then we had some fairly complicated order parameter, that we were using as well. But the idea was that we could get a crossing once we come off that line, but if we're back on the line, we can't get it to happen. And that was essentially the observation.
So what is this W? Because there's no W.
The W was like, it's really like, I had terms like C dagger, X, plus 1, and the W was really like the weight in front of those. So there's a Hamilton. Oh, it's not. It's dark and this is red.
There should be boxes of them behind the blackboard.
Oh yeah.
It's just the.
Yeah. So like my Hamiltonian here is like C dagger X 1 plus the Hamilton conjugate, and what the W is basically the overall weight in front of that. The size of the, so it's just kind of setting the size of the hop. I mean, it probably wouldn't have made sense. It doesn't make sense to have 3 parameters there. You can always rescale one. But this is, I guess this is the legacy of the way other people did it. So, yeah. The W you could set to equal. So that's this is a little digression, but it's an important thing. It's an important aspect of why I went to expect the next few months to do something. So one other thing I want to tell you about is, this is something that we observe, right, on our computers. But when was the problems of actually seeing something like this happen in real life is kind of an issue that people come up with in quantum information all the time. And it's called the postselection problem. So for example, this is a slightly different kind of picture I have in mind, but if you imagine a quantum circuit, there's some unitary evolution. But now I'm going to have some stochastic processes where I'm going to be some randomness, and then some more unitary evolution, some randomness. It's pretty much the same idea as what we're doing here. And the issue is, if you have a quantum computing, a computer, the idea is that you would do the same thing over and over, like each time. You would measure at the end, do the same process, measure at the end. And you can build up statistics because you get the same state at the end of each of the unit of things. But if you have an inherently random process inside in your evolution, you never get the same state twice. If you go to a very, very large system, then you're randomly, changing it every time, and you fill up the space of all possible states, but you basically never get the same state twice. So you never have an opportunity to do something like tomography. You can't build up statistics on how the state works. So, so that's the basic idea behind the postselection problem. If we were to try and observe these transitions on an actual computer in a real device, I mean, we'd have to somehow be, have done this exact same process multiple times, but somehow magically achieve all the same measurement results at every single time that we did it. And it's very unlikely for that to ever happen. And so although this is like a real thing that can happen, it seems that it's a very, very difficult thing to, at least to model or to check on an actual quantum device. I'll say a little bit more about that. And so this partially motivates them what I want to talk about is in terms of this replica idea. And so this is more or less the story I told you already. If you have a density matrix, you want to measure an operator, you take the trace of that operator, or the trace of the density matrix times that operator, you get the expectation value. And that, in principle, then, in the limit of infinite number of trajectories, you could get that number from just taking all the individual from each trajectory, taking each one an average of each trajectory. And of course, you could define your density matrix as basically being the limit of all the trajectories. You could take the outer product, and that density matrix would be defined like that. And then it'd be, you have this perfect matching between these different things, but still would effectively give you all the same, this row tilde would give you all the same information as row. And so those two things would match up in the limit that the infinite trajectory. But let's say now you want to get this quantity. So this is what I mean by some higher order moment. I can calculate this if I have the trajectories, right? I'm taking the expectation value of each trajectory, I'm squaring it, okay, I'm taking then the expectation value, but summing over, in this case, that they all have equal weights. But I can get that number. But I can't just go in and take that density matrix times, let's say, n squared, for example. That's not the same, it's not the same thing. In this case, for example, if n is a number operator, it would just be also n squared would be n. So you wouldn't get any extra information. So the question then is how do you get those higher order moments out of something like a density matrix? And so that brings you to the idea of what I mean by a replica density matrix. So let's say this is the normal density matrix, the one I mentioned before, the one that you would get from summing over all the trajectories. And I'm going to call that like rho, and I'm going to give it a superscript R1, meaning like one replica density matrix. And then I'm going to define the second replica as basically take all my ensemble of states, but then I'm just going to take the same sum, but I'm just going to do the Kronecker delta of each one of those inside. And so now that's going to be my two replica. Again, going to the end. And likewise, you have the three replica density matrix, and you have the four replicas. And so this is how you define it. And it gets a bit easier it gets a bit unwieldy to carry around all these data products. So what you can define is, let's say, a conditional density matrix, which is like the pure state density matrix that you just take the outer product of each of the trajectories. We'll call that rho superscript C. And then you can put it like this. It's a bit easier. I can get rid of the sums, all the sums over all the things that just turn them into. I can just take the bars over them. So this is the notation I want to use for some higher order replica density matrices. So I'm just taking the Kronecker product of every single trajectory and then averaging over the whole lot.
But so these are the same time for each level.
Yes, it's the same. Yeah, it's the same set of states. Just now you're Kroneckering as you go along. And you're summing over the tensor products that you made.
Yeah, same state.
Yeah. So there's an ensemble of states, and you could, if you have the ensemble of states, you can construct, yeah, any of these things, you know, everything. And so you probably, so that's all it is. It's not, there's nothing else to it, and there's no real fancy tricks to it, but that's what the construction is. And it has some properties that like can be instinctive to you. Like if you trace out one of those replicas, if you trace out, you have this big density matrix now. If you trace out, let's say, the subspace corresponding to one, you basically just retreat to the lower level density matrix, right? So you trace out any of them, you'll get. So if I start with the row R4, trace out one, I'll come back to row R3. And you can repeat that process. It doesn't matter which thing you set. There's perfect permutation symmetry between each of the elements in the replica space. So here you can basically trace out anything, and you can kind of know how it's going, where it's going to go. It has to have that property. So for example, if I trace out 2 of the copies, let's say of row R4, I get back to row R2, and you keep going. And you keep going all the way down. If you trace out everything but one copy, you end back up with the density matrix, the row R1, which, if you remember, is the thing that in the Lindblad equation, for example, that's the thing that you're evolving forward in time, at least on the average in the limit of infinite number of trajectories. So that's how it goes. So yeah. And then if you want to see then how you get the higher moments from those things, how those objects would allow you to get these higher moments is relatively easy. So if I want to take the expectation value, so I want to say that if I like, I like to think of it like this. Like I have a row, so this is like the way I think of it. So a single copy is just a 1D chain. I mean, it doesn't have to be a 1D chain, but just imagine it's a 1D chain. And then I'm going to take the second copy, I'm just going to come in, I'm going to tensor product that second copy on that occupies a space, a space that's now bigger. And you know, I can then work on that space. That's my new Hilbert space that I want to work on. And in particular, if I want to calculate something like this higher order moment that I mentioned before, so in this case I'm calling it nx squared, for example. And so you basically take row R2, and then what you want to do is you want to take the expectation value of that row R2 with, you know, the operator on that side and the corresponding one on the other side. And so that then allows you to, you can then kind of work through the calculation. You end up moving some stuff around with some algebra. In the end, you get the thing that I mentioned before. You end up essentially getting a sum over the square of the expectation values, right? So you're able to pull out these higher order moments, but at the cost that you have to double effectively your Hilbert space, or double the number of sites in your Hilbert space, which is even worse. Okay. So yeah, you can go again. You can imagine getting third order moments in the same way. You have to have 3 copies of the thing, and this would allow you to calculate this in 3 correlator, get 5. You can also do some complicated cross correlations between the different things. So as long as you have the replica space, you effectively have access to all these higher order quantities. And one maybe important point is if you do something like this, where I'm looking at some correlation on just but the operators are just on one of the replicas. There's that's kind of a redundant thing because, like I mentioned before, you can trace out the other 2 things. So if you're only on one replica, then you must get the same. Or so if you just look at one replica, you must get the same answer as if you just didn't make the thing in the first place. And that's an important point because it tells you that somehow all the expectation values that you could get from one replica should also be exactly the same values on the higher replicas. Like that's the kind of key point. And yeah, and a few other properties. I'd say yeah, this is it. There's also again the property of permutation symmetry, right? So if I look at this particular correlator, so I have an operator on the second replica, I have an operator B on the third replica, and if I flip them around, then it will be the same answer. But again, you have this permutation symmetry. It's inbuilt into it. So yeah, so that's essentially the moments. And then, but you can do more. You can also get things like entanglement entropy. So you can just read off the entanglement entropy from there. But you can read off something related to entanglement in the replicas. So this is what people sometimes call a swap trick. So if you imagine you take the operator, consider the operation, let's say, that is going to swap all my sites with the corresponding sites on another replica. So like I'm literally just going to imagine swap expectation value of that swap operator. The expectation value in this case being trace the row or squared times the swap. So it's important that you're not acting with the swap operator on the density matrix, you're taking the expectation value of the swap operator with the density matrix. And if you calculate that, it's relatively easy to see, for example, that that's related to trace row squared, which is essentially your purity. But the nice thing is it's essentially the average trace row squared. So you're taking the average purity of your system. So that's the average, like, it's related, the purity is related to entanglement, and so it's kind of telling you how on average in the replica space you could get something that's like entanglement. And you can also do something like partial swap. So if you consider the partial swap, where you just take half the system and swap it with half of the other corresponding replica. In that case, you can go through something and you can get essentially what's your average partial purity. So you can get something like, basically you end up effectively taking a trace of your system and you end up allowing it to calculate the purity of the reduced density matrix. And that's really a measure of, let's say, entanglement between A and the rest of the system. And you can relate it to the second Renning entropy. It's the second Renning entropy is this thing here, but it's not quite. It's the same if it's a pure state, but in this case, you can see the average Renning entropy would be taking the average over the log of trace row squared. But the fact that you've got is the average of trace row squared, so you can take the log of that and you can lower bound effectively the Renning entropy. Okay, so now I want to talk about like master phase. So hopefully that's like reason clear as to why you would want to do this. You know, it gives you a lot of information, and then it might be clear. Like since you can do all these things, it might be nice if we could write down an equation that involved, let's say, these higher order replicas forward in time, without taking all these stochastic dynamics. So we're looking for a master equation, like the Lindblad equation, that basically allows us to evolve forward this row or two. And so this is where I show you now how it works for a single replica. So if you take the normal trajectory method, there's the Schrodinger equation plus these extra bits associated with the noise or the measurement. And what you do is you can write that in terms of these conditional density matrices. This is exactly the same. These two things are exactly the same thing. So if you work with this equation, this is going to tell you how to take moves forward in time. And then what you want to do is, right, you want to take the average of all these things, right? So you take the average of all these conditional density matrices. So here I'm just putting a bar over everything I have here. And you can then use the properties of the Wiener process correlations up there on the right hand side, and you can reduce it down to something that looks like this. And it's starting to look a little bit like the Lindblad equation, right? It's looking actually very like the Lindblad equation. But this is kind of a trick. It's not there yet. Because if you look at how I define these operators M, the M are defined as these O operators minus the expectation value of the O operator. So it's actually, if I had this equation, but instead of the M's I have these O's, then I'm done. But I don't have that yet. So what you do is you continue. You shove in the value for M into each of the subparts, right? Shove it in there. And you've got to put in this, and then you get something that looks like this. And then if you take the second term, the one on the right hand side, that's what that looks like. I'm shoving an M there. And then that looks like this. And then there's a very important thing you could, well, first thing I suppose is to look at the two top terms, right? The two top terms are like an operator O, and the bar is over that. But it's an operator, it's a fixed thing. So I can effectively move the bar off fixed operator just onto the density vectors. And likewise, I can do the same on the other side, right? So I can I can fix that top bit. And then there's this kind of crucial cancellation that you have. You see that there's these terms here, which are not nice, right? I can't remove that the bar is stuck over these expectation values. It's like you're sticking the expectation value statistical properties together with the statistical properties of the density matrix, and I can't really write that as rho or 1. But because the two terms appear with a minus sign on an opposite sign, I can just get rid of them, and they cancel. And so you then get to shove back in the two O's back in, and that's how you get the limit equation. So the limit equation pops out. So that's how it works. And so I'm just going to use this kind of L to define the limit equation. So that's what it would look like. And it's something very nice about how that works. But you have to remember that there's that nice cancellation that happens. And somehow, you know, as we'll see in a second, it might not happen. It doesn't happen. Higher order. And so if I want to do it now for second order density vector, so now I want to try and do the same thing. I want to involve this R2 thing forward in time. And it turns out you can kind of break it up into different contributions. Right? So one where you effectively jump forward on one replica, plus where you effectively jump forward on another replica, and then the third term where you jump forward, let's say, on two replicas at the same time. And then it breaks down like this. The first and second terms just look like, imagine I just did a limit equation on each of the copies that I mentioned before. But I have this cross term, so this third term ends up being this thing here like this. And yeah, so you've got to deal with that last bit if you want to understand what's the two replica master equation. And so if we have a look at, so like I said, this is like just like a limit on that guy. This is a limit on the bottom. And then this thing here, and the different terms M come across with the same subscript, but they're operating on two of the different replicas. So there are terms that effectively appear in my equation, and they kind of walk across my system at different points, but they connect the terms that basically end up entangling essentially the two replicas together, which is interesting in itself. And so you've got to, if you want to understand how, the idea would be that we're trying to do the same thing. We're trying to take that sum over all the different trajectories, and we're trying to break it down into something that just has rho or 2, right? We're trying to get that expression out. And okay, so it gets a bit messy. This thing breaks down. When I do the same trick, I put in my m's, I end up getting a bunch of terms. And I don't know if this is what I'm trying to get down to. And you can see here on the first term, I can just see that this rho or 2 is just basically just sitting there by itself. So I can just write that in. So I have something that works there just fine. But then I have these other guys, and this is the same problem that I got around the last time because I had the nice cancellation. But there isn't anything to cancel.
Can you go back just to the cancellation?
Yeah.
Effectively, it seems to me what's happening is you've got Leibniz rule working in this case. I just wanted to see why was Leibniz working. Because I didn't expect it.
Okay.
Leibniz would be, if I've got a commutator term on its own, that Leibniz commutation involves Leibniz, but it's quicker. Something in action on the left and right, and that isn't.
Yeah.
So I don't expect.
Yeah, it is kind of surprising actually, but yeah, I mean you can work through it. I'm not sure. Maybe it could be something to do with the fact that I don't think I'm assuming anything about the operators O, although I intrinsically assume that I'm measuring, so I assume they're Hermitian or something. But yeah, it pops out anyway.
Yeah. Okay.
Yeah. And so so where are we? Get to here, and then see these last two guys are the problem. I can't remove the statistical correlations from the expectation values from the statistical correlations in the trajectories. So you kind of got to deal with it. So it's really those two guys. You'd like to be able to just move the bar off, and I'll show you in a second. That's what some people do, but in principle you can't. But there's an interesting thing because each of those guys can be calculated on some higher order replica. So I'm trying to do second order replica. So if I want to put in something in that expression here, I can actually the quantity that I can use if I had the third order replica. And likewise, if I had this other guy here, I can calculate that quantity if I had access to the fourth order replica. And so in principle, that whole thing, rather than carrying it around for a moment, can be calculated, but it's a function of this row R2, but also row R3 and row R4. And you can kind of imagine how this goes, right? You need row R3, and then you try and write an equation for row R3, and you need row R4, and you need row R5. And so so you set off this kind of infinite hierarchy of dependency on which of the rows that you need. So that's it. So effectively, like you now have, like as I say, you have a choice. Like you can try to cut it off, right? Or you can just deal with the infinities that are going to pop out. So here's your choice. So this is on one side we're going to talk about just imagine trying to put the replica, like cut it down to 2, and then in the other case you imagine effectively dealing with like this infinite like stacking of all the different systems all the way to infinity, and see can you make sense of how that particular system behaves. So if I go this direction, if we take the red pill, one of the things you can do, as I mentioned, is that's what you should do. You should be able to treat this. But what people have done is the simplest thing you can do is like I said, just take a rubber and rub out that line in between the two things. And it's essentially like you're decoupling the kind of statistical correlations now from the trajectories from the quantum correlation. But because you've done that, because you've now isolated this thing here, you can write it as an R2 times whatever these quantities are, and then you have a closed expression for the density matrix. And then there's so that's what you do if you do that thing, you end up then with this expression, and it's a nice, relatively simple expression that you can work with, and it's closed. One thing I'll point out is it doesn't preserve the trace, what we did. So what you would have to actually artificially do if you wanted to preserve the trace is put in some terms. That's what that extra term is. But that's an important point of this is what these guys, Michael Buchholz and collaborators did. And they argue for it because if you can map the model to kind of like a linear, like a boson model. Like a Dirac, you can map it. So if you're dealing with Dirac fermions, for example, you can bosonize it. And then the argument was that you should be able to do this. And they came up with this pretty complicated expression. But they did find in that expression that there's something that looks like a BKT transition. And their argument was that, well, that actually kind of is the analog in this calculation of the entanglement transition that we're at.
What's BKT stand for?
What's the So it's I think there was an Nobel Prize given for this a few years ago. So it's crosserless tiles basically. So the K and the T.
Oh, the KT is crosserless. Oh, okay. Yeah, I know.
Yeah. So you can imagine that if that's true, then they've kind of effectively proven that there's a phase transition. As I mentioned before, if you remember the diagram that I mentioned before, this was for a model of relativistic fermions, but nonetheless they showed the argument was one there. But on the other side of this there's a bunch of work that goes through the infinity set of calculations. And we'll go through it, but again, they map to the nonlinear classes of nonlinear sigma models. And they're able to make fairly kind of convincing arguments that, well, you shouldn't see a transition if you have U1 symmetry. So you have these two different competing things, and like I said, the numerics that we had agreed with this particular method. So like it didn't seem to be something that was there when you had.
Well, surely if you can handle it, this is the right way to do it.
Yeah. They have the ways to do it. Yeah. But I mean, you can handle it with on a very kind of abstract level. That's one of the things, I suppose. But yeah, so then, so to motivate this time, was wondering why doesn't the other thing work, right? I mean, what's wrong with the mean field coupling? So that was really the kind of motivation for what was going on. So maybe the larger question was, is there a way to cut off your thing such that you get accurate expressions and accurate behavior? And what might be wrong with doing the mean field decoupling? Right? So yeah, I mentioned this thing already. The first obvious thing that you can see that's wrong with this is that, like I mentioned before, so this is what I was doing here. If you trace everything out from the 4 replica, you should get the 1 replica. That means that any equation, dynamical equation that you came up with, should reduce to a Lindblad equation at the end. If you look at the so if you look at this equation here, like I said, there's this term on the right hand side that preserves the trace. But the question was, does it preserve all the partial traces? And this thing doesn't preserve the partial trace. And so immediately, what you're doing when you put into the system, you're changing the system so drastically that you've actually not retained what we know happens on average in the system. So you're changing the 1 replica equation. So you get a bunch of other stuff. And so this is kind of a simulation of what you might see. So like here's the Lindblad, here's what you get from trajectories. And then this mean field thing is the blue line, so it's very, very different. It doesn't give you anything. It saturates to the same value, but it doesn't give you the same transit dynamic. If you look at some higher order correlators, for example, this is like kind of a variance cross correlator, you can see it's even more drastically different. And this is the kind of thing you might be looking at if you were trying to see if there was an entanglement transition. So yeah, so what I mentioned before, so I was trying to think, is there a way that you can cut this off? Such that, first of all, one of the first things you want to do is that you want to preserve those partial traces. And so that was what I would then call, like the thing that we're going to try and do is we're going to try and stick on the level of information that we have on the level of row R2. But is there some other way that we can cut it off such that, you know, we respect, let's say, the lower order replica dynamics and basically all the other properties that we focus on. So in order to do that, the basic idea is we're going to take row R2. We're going to use
just to summarize.
Yeah.
If I'm looking at this expression here, what the other ones were doing was effectively replacing this last term with
a different term, yeah.
Just a different term that preserved the trace.
Preserve the trace. Well, actually, it was a different term. And then they added in another one that preserved another term that preserved the trace, but none of that stuff preserves any of the partial traces. Yeah. So what you want to do is try to come up with something. Use row R2 to come up with some expressions for these estimates of these higher orders, right? So that they're there, and then you know since those things are just functions of row R2, then you've closed it effectively. So then you have that closed expression. So how do you do that? So the first thing that I'm just repeating myself again, but one of the properties that I mentioned before was this permutation symmetry within your system. If you measure a particular expectation value on one copy on one replica, that's going to be the same number if you measure the same thing on the second replica. And you also have permutation symmetry, right? So if you do this particular thing, this particular expectation value, then you would also see it on all possible permutations of that, and you know, so on and so forth. And then to show you then how you might try to construct your estimate for these higher order replicas, just based on information from lower order replicas, and just a kind of a notational thing. I'm just going to use. I need an inner product for operators, so I'll just use the split inner product, and I'm just going to use these curly brackets to indicate the trace for operators. And then, you know, you can see that if you have some density matrix on any particular order, you can decompose it into some orthonormal subspace, or orthonormal set of operators, right? That fully basically covers all your operators. So that's all I'm writing here. And so let's say that I have some row R3, right? I have some higher order replica. and I want to, you know, fill it in. I want to find out the information that's in there, right? I can, if I start taking expectation values, right, of operators, I can, since I have row R1, for example, I know I have it, right? It's already something I have. I can get the weights of that operator, so I can basically start to, you know, fill in different parts of the system, and kind of that must be correct, right? And so I can gradually build up a picture of the operator, at least in terms of anything, any kind of operator that sits on two replicas. I can get accurate information about that, and I can say that that operator must be in row R3, right? With exactly the weight that I need it to be in there. So I can kind of gradually start to fill up a picture. And if I have enough of that stuff, you know, I can gradually start to see what row R3 might look like. And obviously, if I can go all the way, if I can then start taking all the possibilities of operators that sit on all three replicas, then I can get a full picture of the system, and okay, I just get a full resolution, and eventually get back to the full system. So just decompose it in this particular basis. That's all I'm saying. And then the question that we're trying to do is like, what could you get? So suppose you couldn't look at any of the operators that sit on all three replicas, but just sit on two. Any permutation or any possible like rotation of those guys, you just have that information. So then you try to fill in that information, and that's the question: like what do we get some information from row R2? So it's maybe easier to think of it if you vectorize it. So I can imagine vectorizing my operator row, and I have some set of data. I have my row R2, I can fill that in to a certain value, and then there's a bunch of, so like they're my known knowns. I have my known unknowns, there. And then so I need to know those guys. I need to figure out those guys. I have no idea what, right? I don't have any access to row R3. I need to fill them in. There's no one way or the other what they should be. But if I can do all that, if I've done that correctly, then I know that if I take the partial trace of any one of those two things, the lower replica information is correct when I reduce down. So that's one of the criteria. The next thing that you could ask then is, okay, are these row R3 physical? In the sense that, you know, we know that if they're density matrices, then they should have trace 1. And they should be positive semi-definite. And there's nothing in what I've said that guarantees the second property. The first property, the trace 1 is in there, because the identity is one of the operators that I would have taken the expectation value of. But the positive semi-definite property is just not in there at all. And in fact, it turns out it's just not something that's fulfilled generically. That might seem like a bad thing, but it's actually a pretty useful thing, because it tells you, it's a piece of information about the space that we don't know anything about, that we now have. We can kind of use it as a signpost to say, okay, well, I need to manipulate these weights, but I need to do it in a way that makes my overall thing positive semi-definite. It gives me a pathway, or many pathways back to something that could be more fit. So yeah, so those are the kind of two properties that you want to do. There's a technical bit which I've kind of gone through. I don't have to do this thing on the full space. Like I mentioned, this permutation symmetries. So the problem can be reduced down significantly if I project to permutation symmetric bases. Yeah, this is never an easy slide to do, but I just basically focusing on, let's say, the two replica. I can look at the permutation symmetric subspace there, and I can relate each of the two replica permutation symmetric spaces back to the real data, which I mentioned must be consistent between any replica, and then I can go to a higher order permutation symmetric space. So it's a technical trick, but it allows me to get this in a computer.
So what were the V's and
So imagine I have defined the set of
the representations of the permutation group or something.
Yeah, exactly. For the two replica, the set of states that, given whatever symmetry you're in, the set of states that are permutation symmetric, project onto those. So, like, look at the problem there. And what you wanted to be able to do is within that projected space for the 2 replica, translate that information onto the projected space for the 3 replica. But that's, so it's like a technical thing. And then in order to do that, you basically should go back to the full space where the information is always consistent between the 2 replicas, and you just use that as a bridge between them. But it's an important point because it allows you to like quickly transfer, basically transpose information from a 2 replica to a 3 replica, or 2 replica to a 4 replica, and in a way that's efficient. So all that stuff I mentioned is basically preserving the partial trace. That's one of the features that we said was necessary. And then, okay, the rest of the stuff that I wanted to do was to try to figure out how do I get in the force deposit semi-definite structure in there. And that's not an easy problem. There's a lot of, even though you reduce it down, there's a lot of free parameters that you can play around with. And so we tried a bunch of different things. I found out about a thing called semi-definite programming. I also tried mixtures of hybrid approaches where you use trajectories together with the master equation. That one was like something like this. I used the trajectories to effectively stabilize the master equation, and so you can kind of see that here. But it wasn't very satisfying because I had to calculate trajectories, and the whole point was I didn't want to calculate. And so the question was, is there something better? And I think there is, like at least a little bit better. So this is what the final, say, algorithm that's in the paper does, or the final approach in the paper does. Let's say at a particular time step, I know my rho R2. And the next thing I do is I make an ensemble of pure states, like just a random ensemble of pure states. It should have the same symmetry, right, as the rho R2, as the thing I'm trying to do. But apart from that, it's just a random ensemble. And because I know that, because I define my ensemble, I can now construct this object, which is effectively these replicas from that ensemble, with some probabilities p, which I don't know. But because I can make that object generate for any replica from this just random, purely random ensemble that I have, and I can try and find the p, these probabilities that basically maximize the overlap with the thing that I know. So I kind of force the second order correlations onto the distribution of my just random set of states. That's the first thing, and then of course so that gives you the pi, and then those probabilities pi then allow you to construct estimates for the higher order replicas, the third and the fourth. And so that's the first step. And in fact, if you had enough in your ensemble, enough states in your ensemble that you could make this thing one, then you don't need to do anything else. So that's what you probably should do.
Where did this side microphone do you generate that?
Just generate them, yeah. So it's like so it's interesting what you can do there. That's what I'll tell you in a second. But yeah, so you just make them. I used Gaussian states, even for interacting problems, and it still works. So you just need to have a sufficiently high number of them. And then so you can use that to construct an estimate for the rho 3 and rho 4. And that's like completely dependent on rho R2, so you effectively compose it. But one last thing, you can then ensure the consistency with the lower order things from using this information. So if your information hasn't quite matched with rho R2, you can then just basically transpose the things that you do know for sure onto the estimate for rho R2.
So you're putting essentially non-interacting ansatz for the higher rows.
Yeah, you don't have to, but you can. Yeah, seems to be you can.
But that's the answers you're using here.
Yeah.
And that seems to be the good.
Seems good results. Yeah. I'll show you in a second with the numbers. I'll just and so yeah, that's it. And then you have a closed equation, so you can just move forward to the next step, and then you can just go. So just to show you the test. So this is this is hardly, it's a success because it works. So this is just showing the consistency with the Lindblad. And you can see the mean field decoupled one is bad, right? So it doesn't work. The corrected one basically sits, it's guaranteed to sit exactly on the red line. The red line is, sorry, the green line is an invalid, and then the red sits like identically on it. It's by construction, it can't be any different. But then these high order correlations, it really matches up well. And then this is one where the V here was like an interacting term, like a four fermion term. That was the weight in terms of it. So, but it was using a Gaussian ensemble to stabilize it and it worked perfectly well as well, which is quite interesting. This is the estimates for the, like I said, the Renyi entropy. So I said, okay, the lower bounds it. The actual Renyi entropy is the dashed line. I don't know if you can see it. It's on top. But then the estimates for the purity, the average partial purity, together with the trajectories, you can see it works pretty good. And it's, you know, it's a one-shot calculation that, you know, compared to in this case, thousands, I think about 4,000 trajectories, and then it works for various gamma. You can kind of see the effect of higher gamma there, you know, pushing down your time entropy. Just in terms of estimates for numerical tests, it's not extensive, but obviously you would hope that this gets more accurate as you compare it against more and more trajectories. And what I found is it tends to saturate around the Trotter error. So like it works up to whatever numerical artifacts are in the problem in the first place. But a bunch of different ones. I use a couple of different measures. This is essentially it goes down, but it doesn't keep going down. So there's definitely some. It's not perfectly accurate, but it's not too bad. So yeah, so that's it. Just a summary. So like I said, we force the consistency of, like in these higher order replicas, we force the consistency of lower order things by just focusing on the partial trace. Particularly, we were kind of focusing on like the null space that's in the partial trace. And then that allowed us to kind of circumvent this hierarchy, this infinite hierarchy of replica equations. At least it looks good for on some small systems. And again, so the important point is now you've effectively there's a way that you can get information about the average entanglement entropy in like one shot without having to do targets and trajectories. And somehow there's a closed equation that allows you to do that. And I think that's kind of interesting just in and of itself. For future work, this is like a system 4 qubits, you know. So it's like just to tell you how, like, you know, how it's going to scale. Like, so for 4 qubits, this is just the dynamics of a system size that is 16 by 16, right? And so, you know, if you do the trajectories, if you have to deal with fourth order replica, suddenly now you have 16 qubits, and it's like 65,000 matrices. So it really scales horribly. And it's not actually that bad. So there's projections to subspaces and things like that. But if you wanted to actually extend this to large system sizes, you've got to put it inside, embed it in some other numerical system, like matrix product states, for example, which might allow you to build systems. So the best current method is to use this fixed stochastic ensemble to estimate the hierarchical states. It's important that, so if I had interactions, if my Hamiltonian was interacting, it still works to use a Gaussian ensemble, which is pretty interesting. It just seems that you just need to have a sufficient spread of states for it to work. It would be nice to maybe just figure out, like what I'm trying to do at the moment, maybe as a summer project, is to just figure out, to understand my ensemble a little bit better, like don't make it random, like fix a set of states and see how does the thing behave. A nice way to maybe understand it would be, you know, if you consider it in quantum information, people talk about T designs. So it's like what it's property that the ensemble might have in terms of what type of higher order correlators it can represent. So trying to understand the accuracy of the system as a function of the T in the T design will be a nice way to go. And yeah, so that's.
So what do you mean by Gaussian ensemble?
So start with like a vacuum state, let's say, and then I'm allowed to do unitaries on that state, random unitaries on that state, as long as they're like I use quadratic number of fermions on the side that generates the unitary. So anything I can make with take an arbitrary quadratic Hamiltonian, any unitary I can make from that essentially is what I mean. The state then that I can make from that collection of unitaries. So I cannot, like, I definitely cannot have, there's no interacting parts in those states. I've kept my Hamiltonian quadratic.
So the states of quadratic form.
No, not even. Like they would be valid, yes. The eigenstates of the quadratic Hamiltonian would be valid states. But it's more like the way I generate them is I throw down a random quadratic Hamiltonian, make the unitary, apply it to the vacuum state, and that's my state. That's one state in mind. And then I throw down another random quadratic Hamiltonian, make another state, and that's another state in the example. What you want to try to do is people talk about Gaussian higher ensembles. So you want to kind of distribute
You just the coefficient.
coefficients, yeah. But it can only be, it has to be like, quadratic terms. So C dagger C's or C dagger C daggers, Hermitian conjugates. But that's all you're allowed.
Ignoring the nearest neighbor.
You can, it can be long range, it can be anything you want. Anything you want, but just, has to be two.
So it's just quadratic.
Has to be one body, like one body operators.
If there's anything that might be lost by restricting yourself to that class.
Well, I don't understand. I was happy it worked. But it only works, right? So one of the things, the interacting term breaks sublattice symmetry. So if I use something that had sublattice symmetry, it doesn't do the job. But it's easy enough to have quadratic state that breaks sublattice symmetry. So those are the states that I generate and then it works. It could be that this just doesn't work for larger systems. It could just be like somehow small enough that I can do it. But I can't get to the larger systems yet to check and see if it works.
You mentioned example where there seems to be a stochastic transition. Can you check?
That's the goal. So one of the things that would be nice to do would be take that model, right, where they did this mean field decoupling. You know the model; it's a two-replica thing, and you can model that with matrix product states. It's a one-dimensional thing. So you could try to model that, see where, like what is it, what type of transition that is. That's not how they did it in the paper, but you could check that. That's another project that I have. It's hard, it's difficult though.
It's the only one.
Yeah.
The spirit of what you've done there, it seems very similar to Schwinger-Dyson equations and cutting off Schwinger-Dyson equations.
Yeah, maybe.
Just again cutting off higher coordinate, and you jump into zero, or guessing an approximation for that.
Yeah, I don't know really anything about that. So
it usually breaks down if you
push it.
Second order phase transition.
Okay.
There are exponents that need to be picked up, and they affect all of the higher coordinates.
I mean, could very well be something like that. Like
I expected there would be special cases where
I mean, I think the state of the art, at least with this question, is to go to the infinite replicas and just to deal with it there. This is maybe academic question, but it's still like it's a nice thing to have it. I think if you could close it off in some way that was there's still. So I'm saying this is a deterministic thing, but it's not really like there's an optimization process in there. I'm choosing these random states, but it's possible to maybe close this off properly and maybe come up these the probabilities that I mentioned that you optimize to find. Maybe it's possible to come up with a nice differential equation for those. In which case, then it becomes an interesting thing to see, like, what does that tell you? But that's something for down the road.
try doing this just for the system at the start where it's really on two sides.
Oh yeah.
There, maybe this stuff actually needs.
Oh yeah. Well, yeah, the two sides. Yeah, you possibly can. I mean, yeah, you probably do something for even the four sides that I'm talking about. But yeah, two sides you still go to 8 in the end, you know.
Sure.
And it's like it's so that's for the four. Like you need to do something on the level of 8 sides in 4. And and the other thing is it's density matrices, right? So it's not. It's effectively 16.
Sure.
when you vectorize it, it's like you know. So it does kind of blow up in your face very very fast. So in terms of dimensionality, the number of different variables in the system.
But if you go back to the part of the post-election problem, right? So there is when you actually find the results from the trajectories that there were actual measurements.
Yeah.
So you really can actually calculate all these funny, averages and squares of things and powers of things.
No, you can't. Like in a measurement, you have access to. Assuming you only ever get the state once, right? You can do one measurement, or you can maybe do some kind of thing where you maybe get some non-commuting measurements from the same state, but you're restricted to the number of measurements you get, and you never get access to that state again. So one of the things you could try to do, another way to do this, is to have try to copy the dynamics. So run one circuit, and then depending on the measurements that you make, the outcomes of the measurements, which you have access, try to finesse another copy to do the same thing. If you have 2 copies at the end, then you can use that spot trick to actually get a one-shot measurement of the entanglement. And there's a way that you can get the average entanglement by doing that over and over again. You don't run into the postselection. That trick that I mentioned is really difficult thing to do. So you're effectively cloning dynamics, right? Which not just cloning dynamics, cloning stochastic dynamics. That's very, very, very difficult thing to do. And so there's an overhead associated, like this computational overhead that just blows up. But you can, it's possible to do it. But yeah, I don't see. I haven't seen another way around it. This is a nice way to get around the post-selection problem, but maybe not on the level of the computer. Some people what they do is they try to have a shadow, classical calculation that they can do. So if it's just Gaussian formulas, you can kind of do it. And there's a few different tricks like that where people have tried to come up with a way to see this experiment. And some people have just brute forced it, they just deal with the post-selection problem. They just track every state and they do billions of measurements and then they have enough. But it's not going to scale essentially to large system size. So yeah. This doesn't necessarily solve it or anything, but it gives you potentially another way to model it.
No, it's great to have a equation that's large to those traits.
Yeah.
This stochastic dynamics.
Yeah.
To the answer.
Yeah. Yeah. It's interesting to me that's even possible. That it works. So I don't know what it actually means, but foundational level. But it's interesting that it's possible.
I was wondering, just generally in this topic of replicating systems, are there other properties apart from the growth of the entanglement attribute that people are interested in? I mean, I think I saw something people call determinisation. So you have your density matrix at the first replica that might parameterize, and then you can ask about whether replicated systems also parameterize and what they parameterize.
Yeah, I've seen some of the stuff on the determinisation too. I mean, that's, I guess, it's kind of an offshoot of this whole branch. The other thing, like I mentioned, it was called an entanglement transition. There's other people who come out from the perspective, you start with some mixed state, and you run the same type of dynamics. What you see is, with a certain amount of measurement strength, it purifies. So it's also called a purification transition. it's the same process. But coming from the other perspective, that's a different perspective, you see purification. That's another thing. I mean, and you can measure from this too, right? As I said, the measure we're looking at is the partial purity, so for purity. I'm trying to think of, is there any other thing that people have looked at it?
No, we're gonna start off recording.